Hi, today in our lecture in presentation, I would explain the optimization and controls of the electrical power, especially for aeronautics and space. That my model that I designed, the algorithm that can be used for NASA, for Canadian Space Agency, and for the aviation like Boeing and Airbus. So my model is a new approach, and later on we can design a chip and hardware to implement this model. So far, this is a software implementation of the model, and if we design in future for my research, we can sell it to NASA, the space research organization, aeronautical companies, huge aircraft manufacturers like Boeing and Airbus and Bombardier, Lockheed Martin, and we can sell this model to military aircrafts and Air Force, like US Air Force, Canadian, European Air Forces, or the Air Force of other countries which are really interested to enhance their aeronautical models. The next generation aircrafts are more towards electrified aircraft. Like they are like more just like EVs. We have the aircrafts and the drones, and they should be more capable of working on electrical system without relying on the fuel systems. This is the approach that I designed in this chip and in this algorithm for the chip. It's a four mathematical model, how we do the optimization and control to make the electrical system more efficient, and for the aircrafts to fly without fuel. Not for now, but in future. Some of the aircraft, they're already flying without fuel. But this approach is especially for the vertical takeoff and vertical landing of the aviation of the military aircrafts and military aviation aircrafts and for the Air Force. If the drones or the military aircraft, they are well equipped, they are good in making timely decision for maneuvering, for moving from one place to another in hard weather conditions, in high altitude, and when the enemy is in front of those aircrafts, how to moderate, how to tackle, how to get the telecommunication signals, how to approach, and if they are not dependent upon the fuel engine, and if they have to do this with just electricity. And where that electricity will come from the air, from the wind turbine. The aircraft will be having wind turbine outside the aircraft and solar panel from the sunlight. So you don't have to worry for the expenses for the fuel for the aircraft, and it will not be fatal. Like if emergency happens, there is no burning of the engine and all that. So let's make it more technical, and I would suggest the air forces, the airlines, the aircraft manufacturers, and the space research organizations like NASA and CSA, they can implement this technology that we have. So let's begin with the presentations. What we will do is this is like a research model, and then the module on the right is like we discussed about the text, the data, the reference papers, and the books we studied. So in this, we will present and discuss various hardware and aeronautical electrical power engineering macro grid issues and challenges. And for the reading module, we will summarize how we created a concrete mathematical model to partially fill the research gaps in these papers, and we will present our contributions in designing new algorithms. And we will provide software solutions through deep neural networks and artificial intelligence based models. So, what actually the issues we have in aeronautical systems, and why more complex these systems are than the Earth-based system? One is the load behavior, the power sources, wear and space, and the thermal management. So why this is more complex than the Earth-based systems? Because in Earth-based systems, flight dynamics cause sudden and sharp. Sorry, in the aviation, flight dynamics cause sudden and sharp load variations, and sources conditions vary with the RPM, altitude, and flight phase. In aeronautical systems, engines, APUs, batteries, RAM, air turbines. These are the issues. Then the weight and the space, strict mass and volume constraints are there. Whereas if we compare it with the Earth-based system, this impacts fuel efficiency that requires ultra compact power components, and for the thermal management, limited cooling in high altitude enclosed structures. Whereas heat cannot dissipate easily, that requires onboard thermal engineering. So these are some of the aspects. And then in aeronautical systems, we have some other issues like environmental effects that prone to arcing, EMI coronas, discharge at altitudes that requires shielding high dielectric EMI filtering. Whereas for the mobility induced transitions affected by turbulence, pitch, raw speed shifts. So these are some of the issues. I will continue from this slide, and we will talk more in detail that how we designed our system and how this algorithm is going to work. Uh, these are some of the reference papers. I took references and I mentioned the research gaps in these research papers. Mostly they are IEEE transactions and the schematic you see on the right. These are the technical diagrams that I will in next few slides. I'm going to discuss those. And for I mentioned it like with issue wise, issues 1 to 3 that we have. I have mentioned those as references, and that if you see those are very recent researches. Um, these are just the references for past 5 years research, because my model, my algorithm is a new design. It's not the old one. So some of the issues from issue number 4 to 7 that I took from these research papers. Mostly research papers are 2023 to 22, and these are some of the issues there on the right hand side, and these are the references for the last few issues. And for the general tools and support, I took help from these two papers. And for the readings, for the books, for my research, I read Smart Grid Infrastructure. These are the URLs, and its impact that helped formulate the system domain. I mentioned the step number, section number, so and so. Then book number 2, the electric power systems, because this is like an idea that informed the construction of the governing electrical equations used in my physics-informed neural network and sections I mentioned here. And also book number 3 that is more related with the physics-informed neural network and MPC predictive model. These are some of the other books. One is related to physics-informed in a neural network, because we have to know the physics of the devices, the meters, the generators, the TRUs, the transmitters, the receivers, and all that. We have to know their physics and the boundaries and specifications. Then we can design our optimization uh, algorithms accordingly. And then the model predictive control system that enabled embedded real-time MPC optimization structure in our model number 2, as we discussed. For aircraft systems, Boeing 787, I especially selected this one because this is one of the most recent aircraft from the Boeing. Then these the two books for electrical and electronic system of the aircraft, and the title electric aircraft dynamics and modeling and simulation. So that contributed to hybrid simulation combining space and analytical systems, and section numbers I mentioned here that help define realistic dynamic input parameters like volt, motor torque in unmanned aerial vehicles, and electronic vertical takeoff and landing scenarios supposed, for example, GNN based flight stability that we will later on talk about those. But what I did is I chose those tools and libraries which were available within the Python, because most of these installations or the libraries or the functions or operations, they are very expensive in terms of getting license. So these are the some of the tools and libraries that DivXDE and Cas8 and Jackco and FNACSX and Open MDAO, which are low like multidisciplinary optimization, and some of the PINN libraries, ML machine learning framework. This is what I use here. Now let's talk about these two pictures. One is the traditional aircraft on the left hand side. On the right hand side, you see the 787 modification. So for the traditional aircraft that uses centralized power system that employs circuit breakers, relays, and contractors, that has an external input to 115 volts AC, and it has an auxiliary power unit that provides backup power. It has power distribution that is mainly manual and heavier. What makes this 787 different? If you see at the right hand side diagram of 787 system, this is like more electric aircraft MEA concept. This has dual generators per engine, a 250 kVA and dual APU generators, and it has an external input power. Then it has AC feeders 230 volts, and this thing minimizes wiring length and weight via remote power distribution, because this RPDU remote power distribution takes care of almost 850 smaller loads. Close to 10 amps or less than 10 amps, whereas the big ones like the dual generators and external inputs and dual, that take care of the heavy loads. Now, let's move on to this colorful electrical system overview, in which auto transformer I mentioned here. This is with the cursor I'm trying to show you. This is auto transformer. Here, there are like six main generators, two from this engine, two from this engine, and one is APU auxiliary power unit. So this comes to one 230 volt distribution, and then it goes to from there to auto transformer unit, and then auto transformer rectifier unit, because eventually that AC has to be converted to DC for the batteries to work. As I said before, these are the loads that I'm showing here with the yellow. 850 loads here, which are smaller loads, and then approximately 25 loads here, which are distribution for with the ATU, and 150 loads here. And these are the details of the there for like for the wing ice protection, hydraulic AC motors, and all that. There are 28 loads. These are all the abbreviations of used in this diagram, and especially the environmental control unit is control system is the one that we will take care of, and nitrogen genetic systems, and these are all new physical environments, which has been embedded and incorporated in Boeing 787 system. So the motors, which are approximately 10 loads, they are run here. That has 270 volt AC distribution, whereas the auto transformer unit that takes care of 115 volt DC distribution further. And the one part of this goes to the RPDU, another also goes to the RPDU, but one RPDU that takes care of 850 volts, and then approximately 25 loads here and 150 loads here with transformer rectifier unit, given to 28 volt DC battery. So approximately 150 loads which are like igniters and the flight decks displays and that kind of thing. Now, this is again what I discuss here. Two engine generators plus two APU generators, output is 230 volts, as I said here. So distribution bus is there, ATRU auto transformer rectifier unit, or auto transformer unit that converts 230 volt AC to 115 DC, and this one converts 230 volt AC to plus minus 270 volt DC. So TRU transformer rectifier unit that converts 230 volts AC to 28 volt DC. This is for the battery. So now this is what we discussed here. Hydraulic electric motor pumps are there, which are very important. Then approximately 10 high power loads are there. 115 volt DC distribution is there. That is ATU that feeds into remote power and distribution RPU. Now, that especially that 28 volt DC transformer rectifier unit that supplies approximately 150 loads, which are those, as I said, DC, fuel pump, igniters, and all that. Because I'm reading the presentation in front of me, so that's why sometimes I'm close to the camera. So, remote power distribution and load management. This is another important avenue here. Remote power distribution units, RPDUs. There are 17 plus RPDUs spread across aircraft that handles this much huge loads, huge technically not in terms of load itself, but the number of loads. So load characteristics, most loads are under 10. So as I said, they are not very huge loads, but lots of numbers. So not only with that, for my optimization algorithm, I'm not dealing only with those to take care of those smaller loads, but for the heavier loads for the machine, for the motors, and for the pumps and other hydraulics. Issue one is centralized load distribution complexity. This is now important. This is not related to maintenance and engineering. This is a real research-based work now. The problem number one that 787 has is that 850 loads distribution across multiple voltage domains with this specification, as I mentioned here 270 volt and 115 volt DC 20. This is an issue that which load needs 28 volt, which load needs 115 volt DC, and which one needs the AC as well. So another is the long wiring network that increase weight and complexity. So in this my model with new algorithm, I'm trying to reduce that weight by using that software implementation. So load imbalances across remote power distribution RPDUs. So that is another issue. Then in my model, that learns optimal load dispatch dynamically using real-time physics and sensor. Once you know the real-time physics, that real-time physics specifications, those actually dependent upon the weather, environment, altitude, air pressure, and so many other factors. So those the dynamics or the specifications or the behavior of those resistors, capacitors, inductors, generators, magnetic fields, transformers, they change and rapidly change sometimes because of the rapid change, because of the maneuvering of the aircraft, banking or yawing or pitching, because of the altitude change, because of the air pockets, because of the climate change. So there are so many. So here in this figure, I have addressed each one of them in my algorithms. So one is the centralized load distribution complexity, its complexity. Another is insufficient power relation and transients that I will discuss next. And then the static fault response and safety margins and poor cross-domain adaptability. So let's move on to the next, and let me make sure that the system is recording and we are still, I'm still with you guys. Yes. So now moving on from here, we can say for issue number two, which is centralized, which is static fault response and safety. The problem in Boeing 787 is that it is like a fixed safety threshold voltage, because there is a threshold voltage which is not physics informed. In my model, I have embedded incorporated physics informed algorithm where the system is not dependent only upon the threshold voltage and current as designed according to the design feature, but according to the physics of the material. That this system in 787 that lacks real-time adaptation during unexpected fault, for example, APU failure, because there are numbers of different scenarios where this system goes down, or it works not efficient. It doesn't work efficiently because of it lacks real-time adaptation during unexpected faults. In my model, in PIN MPC solution, I try to embed real world physics, Kirchhoff's law, Ohm's law, Faraday's law, and all into a neural net constraint. This is the specialty of the neural network and machine learning that uh, embeds real world physics into the system and continuously forecast voltage and current behavior under the evolving load generator conditions. If the load and generator conditions they are changing because of the temperature, because of any other reason, so we have to we have to have a continuous forecast. So what is next is going to happen, and we have to be prepared for that. So in my algorithm, there would be a readiness, preparedness ahead of time. So that and this model triggers uh, uh, proactive fault mitigation via constraints So MPC. So if we are proactive, then by MPC, the next step after PIN network that will take care and will do the model predictive control. Now, for the third inefficient power predictions in transients, this is another issue with the Boeing 787 aircraft of the Boeing. Transformer rectifier unit TRU, auto transformer ATUs handle fixed set of loads because if let's say the load condition goes up and down, it means that TRU and ATRU they are trained or they are equipped with or they have the capability of dealing with the fixed sets of loads. Now, the transient surges, for example, during engine start, gear deployment, or poorly managed in legacy logic, let's say because this is the legacy logic that they have already have in the Boeing. If it is apart from this out of box, is not dependent upon upon the legacy logic, then what is going to happen? But in my pen MPC algorithms, I have defined the physics informed neural networks PINN that predicts load surge and transient dynamics accordingly. And next step to it is the MPC that dynamically allocates generator backup capacity to absorb the transients. Because if there is a transient, there is a change that they will have to have some backup plan that can make sure that this effect is not going to destabilize my system. So this model, my model, prevents undervoltage or component stress via real-time optimization because optimization is happening, but it has to be real-time based. Now, the fourth one that is poor cross domain. There are 10 areas I selected, but I'm just mentioning four of these because it will be too much for this presentation. One problem with Boeing 787 aircraft is, which is the most latest, is that the legacy systems are tightly coupled to aviation specific hardware logic because the computer science specific hard logics and the electrical engineering specific logics, they may or may not differ with what is the specific hardware, aviation specific hardware logic. So in 787, no adaptability for hybrid electric aircraft, UAVs, or multi-mission roles. If the, as I said, for the military aviation, for military aircraft, if the mission is critical, mission is different, but it means your electrical system is not designed for different scenarios. So in my model, I did a training of my model and I designed it and I implemented it, I tested it, and took the visuals with synthetic data, we'll be doing with real data, and we'll be producing a model that eventually we will implement in the hardware. So in this model, this easily integrates with simulators like PX4 is one of the simulators used in aviation and aeronautics, and then Basilisk can open MDAO. These are some of the simulator environments where we can use it. That my model enables artificial intelligence driven proves management and in next generation electric aviation spacecraft or military drones using a single code base. What is new in my model is a single code base for the space, for the aviation, for aeronautics, and for the military aircraft. The whole one kind of with different data, with different missions, but there is a one model that will deal with it. Um, now it's a larger font I can read. One issue is the generator failure, another is DC bus instability, and then the RAM air turbine limitations. The generator failure actually that affects generator L1R2 failure disturbs AC bus stability. Whereas my model 2 solution, the PIN physics informed neural network predicts a drop and the MPC, the model predictive control that reroutes load to APU and RAT. So see what happens when the generator left or the L1 or R2 there is a failure. So the MPC will reroute the load to APU. That will be as predicted by PIN. So PIN will definitely be the physics informed neural network will predict, whereas the model predictive control MPC that will reroute the road to APU or RAT. So research gap in the reference number one in 2020, according to his research, there was no predictive adaptive control during generator overload. Then for DC based instability, I am referring paper number 2, 2021. Garcia and Tang, there is in this paper, there is no coordinated handling of TRU and ATRU outage. Whereas in the third paper of Tang, 2021, no real load prioritization under RAT only mode. So when you do a prioritization, this is not on the real-time load basis. So these are some of the gaps in the research papers that I have mentioned as references. And if you see other papers like for battery isolation, for TRU, ATR, and cross-die conflicts and thermal resistance, there are the gaps. The one is for the paper number 2023. There is there is no voltage signature tracking in battery switching. And then another paper that talks about TRU and ATRs, that lacks real-time section of the backup converters. So in my optimization for the PIN, my system finds best alternatives, MPC rerouting. Whereas for the voltage signature tracking in battery, it's absent there. In my PIN, system detects faults, MPC sequences, and activation safely. And for the cross-tie conflict, my system monitors currents. MPC restricts tie operations. Whereas for the thermal resistance rise, as we see, the effect is resistance increases with the altitude or temperature. So the PIN model RT MPC balances road temperature MPC balances load accordingly. So whereas in this paper of the Jagdeep, there no adaptive current modeling based on altitude conditions. So the another 8, 9, and 10 issue is APU switching surges and component drift and the load shedding gaps. The effect for APU switching surges is the voltage spikes, dips during APU startup. Whereas in this paper, that lacks a transient anticipation in MPC logic. Whereas in my model, PIN predicts surges, MPC applies soft switch control. So this is what my contribution is. And for the component drift, the effect is like capacitor inductor aging effects, like when it deteriorates or by the passage of time it's not working properly. So there is a paper that Zood in 2022 he mentioned, but that lacks MPC doesn't self-adapt to degraded hardware. So it has to be a self-adaptation, which is not there. But in my model, in my algorithm, PIN retains dynamically where MPC adapts real time. And last but not the least, there are so many other issues, but I am just mentioning 10 of them. Load shedding gaps. Load shedding gaps, as discussed in the reference of FILU in 2023, which is most recent research that lacks smart ranking of load criticality during emergency. Because this shedding gaps is effect is non-essential stay powered during power cuts. So non-essential stay powered during power cuts. When there is a power cut, so why we are still running the non-essential loads? So the MPC, my model, with prioritized loads and PIN protects mission critical power. Should be for the vital loads, important loads. And now, just concluding, these are some of the hardware devices in my so I have so far I have designed the algorithms. I'm going to implement this in this these hardware where I will get the voltage and current sensors. So these are NEM HX 59P and HX 1000. That is a these are current transducers and the energy meters with. I'm sure some of the companies mentioning the Texas Instruments. This has PWM output current sense. So this is the like the block diagram how this sensing and measurement layer is implemented for within in between the communication interface and temperature and thermal sensation and aircraft busing monitoring and voltage and current sensor. This is all these four parameters, group of parameters that which is here in the model like sensing and measurement layer. For the temperature and thermal sensors, these are the equipment that we can use PT 100 or PT 1000 RTDs and digital temperature sensors. Aircraft bus monitoring we can do with the KM 500 DAU or voltage input module NIPX IE 4309. And for the communication network, which is this part, CAN bus, BOS standard, these are the ARINIC 429 FEDX. This is Boeing 787 avionics bus. As we say AFDX, those who are familiar with the 787 avionics bus, so this is AFDX Boeing. Then EtherCAT RS485 for real-time controller integration. There we can implement. And how we implement is these are our generators, and then this is our EDG Collins electric distribution and generation, and this is remote power distribution. So the purpose is like to compute the neural forecast and plus optimize control with constraints in milliseconds. As I said, in fractions of seconds we have to decide, because in critical flights in bad weather conditions, especially with the military aircraft and air force aircraft, you have to decide something within fractions of seconds. So the main controller board is there, co-processors for optimization, memory and logging devices, and software stack is there. So there we can implement our model. In next few presentation, I'll be presenting how to deal with the FPGA ARM Cortex and with the Samsung PRO Endurance micro SD 128 GB memory logging, how we do it with the software stack, PyTorch, TensorFlow, PINN, as I said, and CAS AD, GAK, JETCO, and SkyPy optimizer, and these are all used here. And now the purpose is to apply optimized control signals to actual aircraft systems, load motors and battery meters. Because now we're talking about the huge big loads. So where we need a smart switching units, ATNS, SPC, load controls modules, and actuator interface, power converters, and surge and fault protections. So actuation rectified interface layer will be here. That will be a physical execution layer that will be take care of the smart switching and power converters, and eventually for the loads. This is just a huge big picture with different colors of the various position of the aircraft. In the aircraft, the red one shows the AC power here, and the DC power is in the blue, and the loads in the yellow, where we have all the loads, and the green is showing the monitoring and control units. Now, this is a whole further details of the generator over or failure condition, as we discussed before. How we do we the model 2 solution provides a solution with pin forecast, voltage drop, MPC, reroutes loads, and engages backup powers. As I said before, for DC instability, we have covered this in the previous slides. Pin models, voltage behavior, MPC allocates. Now, after designing all that with the Python codes and getting a visuals and the results of the tables of all these are the parts possible, all these issues number 1 to 10 here I'm showing in this slide 4 to 6. For example, battery isolation, TRUA, redundancy loss, or cross tie bus conflicts, and how my system and model will take care of that. So overall, model, we talk about the solution. It's more about forecasting and optimization, error correction, and pre-failure voltage signatures monitoring and balancing the loads, ELMs and FCC regulations and all that. So these are some of the Boeing 787 electrical system issues models. As we discussed before, these are some of the schematics that we discussed before, with the DC bus instability, with random air turbine dependency. Let's say this random air turbine dependency is not there, then the AC bus is instead of going to critical load, there is a cutoff, and instead they are going to the non-critical loads. So PIN is there to decide where it should go. It should definitely be going towards the critical load, for example, the gaming emergency system, not towards the non-critical lights, right? Non-essential lights or something. And the navigational FCC related to radio frequencies and all that should take care of that instead. Battery isolation errors are there. Improper battery bus A/B logic can cut off critical load triggers, damaging current surges during startup failures. So here the issue is that the improper BAT bus logic can cut off critical loads or trigger damaging currents. So my PIN module, that module detects a pre-failure voltage signature. MPC controls battery activation, order, balances, load, and protects ELMs, FCC, and emergency subsystems. So let's conclude here with last few slides that these are some of the 10 issues and these are the effects, and this is what my model PIN MPC will take care of. For the generator failure, the PIN predicts drop MPC reroutes and uses APU RAD. And for the DC bus stability, PIN monitors MPC switches to alternate converters. Whereas for the RAD limitations, that limits the backup power, PIN estimates load MPC shares on non-crucial loads. And this is one-on-one up to the 10. No, integrated framework summary, how Model 2 was designed. This is a very important question. Model 2, this model, physics informed neural network with model predictive control system that developed using real electrical data from Boeing 787 and NASA. As I said, 787 and NASA and microgrids and smart data sets encodes physical laws into loss functions, ensures real-time feedback, safety compliance, and predictive control for Earth space aircraft system. So initially we studied the Earth-based systems and then remodeled it with the aviation-related, space-related models with additional parameters. So the code files are there with that we can share later on, and these are the issues, especially the electrical issues. If we talk the voltage instability, generator switches failure, RAD deployment delay. So these are the solutions that we provide in my algorithm, especially those who are interested in avionics overloads, load priority enforcement via pin state varying. So this is like one of the approach. ACDC harmonics issues are there. My system is like it's a learned non-linearities via pin operator terms. Features enabled in dynamics scheduling for power sources, VFS, GAPU, and RAT. This is variable frequency generators and emergency load shadings and rerouting logics, forecasting on stability before voltage collapse. This is very important. And multi-objective power efficiency, thermal compliance, and hardware preservations. So these are the features enabled, four special features enabled for this model. And now the monitoring, forecasting, and fault recovery. This is very important in it in this PIN components which are used for forecasting like voltage derivatives. I'm telling about some of the formula and equations used here. Voltage derivatives, current slope, and learned physics, early warning before out of range events, real time adjustments, BPC status, and all that. So for the fault responses, drop in the voltage trigger, reduce control, non-essential system offloads, backup breakers, and everything. Reference papers that we used and the gaps, as I mentioned in the beginning, I'm telling the gaps again. For number one, no control integration. Number two, no feedback loop, no actuation, and so on and so forth. And how we did and we were mapped here. So modeling how the system behaves, we first study how electrical quantities like voltage and current with resistance, magnetic effects, and energy storage component. This gives us a realistic simulation of how the system behaves over time, including underload variations. So we are almost at the end of the presentation here, and we will sooner be showing you in next few presentations real hardware implementation. And last but not the least, we have to train our model. We have to teach AI and the laws of physics uh, to my optimization and forecasting model, and the balancing all training goals during training. The artificial intelligence tries to keep all these factors in harmony, producing results that are both scientifically accurate and perfect. Predictive control for smart decisions, real aircraft parameters they have been used. The system is not abstract. It uses real values from the Boeing 787 aircraft. For example, it respects operational voltage ranges and current levels. These real world limits are used to keep all output within safe zones, and especially handling space and extreme conditions. This model also works in harsh environments like outer space or high altitude flight. It takes temperature into account, adjusting for changes in electrical properties during cold and high load scenarios. So this model also takes care of emergency handling and real-time correction. It takes care of speeding up the learning process. It takes care of continuous learning after deployment. The model continues to learn even after deployment. It adjusts to changes in system behavior, ensuring stability even when new conditions arrive. And here in this model, we simulate emergency cases like voltage dips or generator failures. The model reacts instantly by adjusting control actions and rerouting power to bring everything back into balance. And for the project overcomes that, in this project, we created a single AI system that works across smart grid aircraft and space missions, manage real constraints like power limits, voltage drops, and fault conditions. We enable smart real-time control based on both experience, that is data, and physical laws. And next, we will talk about the Model 3 in next presentation. Model 3 is a hedro that is hybrid, adaptive, deep reinforcement, reinforced optimization. So we will be talking about that, and that expands to 20 unified small grid and aircraft objectives that adds EV integration, DEI, landing resilience metrics, and mixed integer linear programming and DRR fusions and convolutional networks and GAN based and scales to multi-domain Earth space UAV aircraft and urban grids. So thanks for the time for being with me, and I hope this would be a great addition in your knowledge. And next time we will talk more in detail.